Okay, so let's start, guys. Good afternoon, everybody. So this is the sign-up sheet for the project demo. If you didn't select the time slot yet, so I'm gonna pass this one. Sorry, I think you have the wrong one because this is for section 2. Yes. Yeah, this is section 2. Okay. So let me start today's lecture. Today is the last lecture and we have interesting stuff. So let me first tell you what I did last time. Last time I explained this program here. Yeah, I explained this program. I explained how can we generate a signal like this one, okay, using output compare. That's what I explained last time. So actually, all what I did, as you see here in the program, let's see, yeah. So as you see here in the program, guys, so all what I said here, this is the number of count for high, and this is the number of count for low, okay? And all what I said, just if you change this number, you can change the frequency easily. You can change the duty cycle easily. That's what I said. So you can use exactly same program. All what you can do, just change this number so that you can change the frequency. And also, so this program, I can say it's like generic program, general, right? So all what you have to do, just change these numbers, okay? And that's what we are gonna do today, by the way. So today, I wanna, here in this program, I'm explaining how can we use output compare to generate a signal, something like that, okay? So what I'm gonna teach right now is, you remember in chapter 3, when I explained the police alarm, how we did that. It was, the way we did it, it was, I generated a square wave, okay, on BT5. On BT5, that's what we did, right? So we alternated between two different frequencies. One frequency, I think the time here was 1 millisecond. Here the time was 2 milliseconds as far as I remember. So I think this one was 500 hertz, 250, something like that hertz, or maybe the other, yeah, okay. So anyway, that's what we did in chapter 3. We alternated between two frequencies. That's why you can hear two tones. That's what we did, okay. So now, I want to do the same thing, but using output compare. Is that okay? Only output compare. So I'm gonna have output compare interrupt subroutine. Once I enable the interrupt of this output compare, so I'm gonna make police alarm. If you want to stop the police alarm or this alarm, if you want to stop the alarm, all what you have to do just disable the output compare interrupt. Okay? Why output compare can work here? Simply because actually BT5 is output compare number 5, it's channel number 5. You got what I'm saying? So here, if I have to generate this signal on using channel 5. Why it has to be channel 5? Because the buzzer is connected to BT5 or channel 5. So you should not use any other channel. Otherwise, it's not going to work because the buzzer is connected to BT5. This is number 1. Number 2, okay. So the question is how I can modify this program. I'm going to do some modification in this program so that I can generate a signal like this one. Okay, that's not difficult. So if you want to generate, for example, 1 millisecond and 1 millisecond, all what you have to do, as you told us, that's easy, just to change these numbers, okay? So these numbers, I can make this number 3,000 and 3,000. Why? Because based on the prescale is 8, as I explained last time, the time for one count is 1/3 microseconds. This is the time for one count. Is that okay? I think something is wrong here. This is the time for one count, yes. So if you divide, let's see. So if you divide, I think it's okay. Yeah, it's okay. So because if you divide 1 millisecond, you divide it by 1/3 microsecond, you are gonna get 3,000. Is that okay, guys? So number one, if I want to generate 1 millisecond this way, if I want to generate this signal as I did in chapter 3, all what I have to do is just to change this number to 3,000 and 3,000. That's easy, right? Easy, okay? Number two, if I want to generate a signal like this one, all what I have to do, I have to use two different numbers, 6,000 and 6,000. Okay, so that's exactly what I'm gonna do. I'm gonna use these two numbers for half a second, and then I'm gonna use these two numbers for half a second, so that I can generate a signal like this one. Okay, someone can ask me how I can know if this is half a second and this is half a second. Okay, similar to what we did in chapter 3. What we did in chapter 3, I counted how many iterations, okay, should be in one second. We will do the same thing right now. Look here, guys. If you remember, if you remember in chapter 3, what we did, I told you in every iteration we're going to generate one cycle. Okay, for half a second, you should have. Let me remember the numbers. I think 125. One of them was 125, I guess. I don't. Okay, and the other one was 250. Is that okay? Yes. Now I remember the two numbers. Okay, so in order to run this signal, for half a second, and this one for half a second, so I have to generate how many cycles here. We found here it has to be 250, and here it has to be 125. Okay. So now, how I can do the same thing here? That's very easy. Why it is very easy? Because in every cycle, there are two interrupts. Interrupt here and interrupt here. Is that okay? So 125 should be equivalent to 250 interrupts. 250 should be equivalent to 500 interrupts. What do you mean exactly? I mean I have to count the interrupts, and then I have to use this one which is equivalent to 1 millisecond. I have to use this one for 500 interrupts, and then I have to switch to this one for 250 interrupts. Okay, and then repeat again. Okay, so let me summarize what I said in just very few sentences. Number one, I want to make a police siren, so I have to generate a square wave with a certain frequency, as I did in chapter 3, using output compare 5, because the buzzer is connected to BT5. This number one. Okay, so what should be the frequencies as we did before? 1 millisecond and 2 millisecond, which equivalent to 250 hertz and 500 hertz. Okay, so what are the numbers I have to use to generate this kind of signals? I did the calculations. I found it is 3,000 and 3,000. This is in case of 1 millisecond, and in case in 2 millisecond, which is 500 hertz, as I said. Okay, so it has to be 6,000 and 6,000. Okay, that means I have to alternate. I have to change these numbers. I have to alternate between this one and this one. Okay, so but as we did in chapter 3, I ran one frequency for half a second. So I have to run it for a certain time. So how can I get half a second here? As we did in chapter 3, I had iteration. In every iteration, I generate one cycle, and we found that in one of them I have in order for half a second, it has to be 125 cycles. Okay, I'm gonna do the same thing right now, but it's not cycles, it's gonna be interrupts. So here, this one should be interrupted 500 times. After 500 times, I have to switch this one. After 250, I'm gonna come to here. That's how I can alternate. Okay, so you will see it right now. So what I'm gonna do right now is I'm gonna modify this program a little bit. I'm gonna modify it. The way I'm gonna modify it is, okay, I'm gonna generate two frequencies, okay, by alternating between this one and this one. Also, I'm gonna use a counter to count, okay, how many interrupts, because after 500 interrupts, I have to move from here to here. After 250 here, I have to come to here, so that you make half a second here and half a second here. Okay, this is exactly what I did in the program. So here I'm gonna just modify this program. So I'm gonna go show you what I did here. For sure, again, like what I always do, you have here assembly and you have here the equivalent C. I'm gonna explain the C. So as you see here, guys, this is what we have here. This is similar to the program we have. I just added two new variables here. Okay, the first variable is a counter. As I told you, I need to count how many interrupts, because for one frequency I have to count 500. For the other frequency, I have to count 250, okay? Because 500, I'm gonna run the signal for half a second. 250 is gonna be half a second for the other signal, okay? So that's why I need a counter. That's why I define here a counter, okay? Also, I need to know if I'm generating high frequency or low frequency. I need to know, okay? Because I'm gonna generate high, and then I'm gonna go to low. Then after low, I have to go to high. And then after high, I have to go to low. So how I can know if I'm high? How I can know if I'm high and have to go to low, or I'm low, I have to go to high? How I can know? Okay, very easy, as we did before many times. I'm going to use a variable. This variable should have the value, for example, 0, 1, 0, 1, 0, 1. It should be this way, okay? So this program is exactly similar to the program I taught before. The only difference is this is number one. This is one difference. I need two more variables this way. Number two, as you see here, guys, this is inside the interrupt subroutine. So what I did here, as you see, every time I'm gonna increment a counter because, okay. And then, yeah, this is the new part. Everything else is the same. This is just a new part here, okay. So what I did here, guys, I'm saying if the frequency, if again, as I told you, the frequency should be 0, 1, so that one time here, because I'm gonna generate two different frequencies, okay? So if I'm gonna say, if it is zero, and the counter is 500, remember, as I said before, one of them should be 500, right? Yeah, here. So one of them should be 500 interrupts before I move to the second one. The second one has to be 250 before I come to here. Is that okay? So I'm saying here, I think this is the low frequency, right? So yeah, this is the lower frequency, right? Or this is the higher frequency. I think maybe I'm making some mess here. Yeah, because the lower the time is the higher the frequency. Sorry, the lower the time, higher the frequency, right? So this one should be, I think, 500, right? And this one should be 250. That's okay. Okay, so here what I'm saying, yeah. So here what I'm saying, if this one is 0, and I already made 500 interrupts, so 500 interrupts is equivalent to 250 cycle, as I explained in chapter 3, which is equivalent to half second. So because I want to run one tool for half a second, so what should I do if these two conditions are true? So number one, now I'm gonna move to the other signal, which is 1 millisecond and 1 millisecond. Okay, this time counter has to be 0 because I need to count for another 250 for next time. Okay, and then the signal now I'm gonna move to the other signals. That's why I put one here. Okay, and then this subroutine should be interrupted 250 before I come inside here again 250 times. Okay, so after 250 interrupts, now this one is gonna be, I'm gonna switch to 6,000. Okay, counter is 0 because I need to count another 500 here before I come here, and then now the frequency is 0. So exactly what happens is one time here, okay? I have to come to here. So after, to change from one frequency to another, same thing here, to change it from one frequency to another. Is that clear? Any questions? Okay. I see it very interesting because you can do the alarm using one interrupt, using one output compare. You got what I'm saying? So once you enable output compare, you have the program. You can try the program. The program is working. Okay. So once you enable the interrupt, you can hear the alarm. If you wanna stop the alarm, just disable it. Very interesting, right? And the main program is free. You can use the main program for something else. Okay. Any questions? Okay, guys. Any questions? Two things here. Number one, how can we make half a second as we did before? How we did before in chapter 3, the way we did it before, I controlled how many loop, because in every loop I'm gonna make one cycle. Okay, here it is the same thing, but instead of, because I don't have iterations, before I used number 125 to make half a second, and for the other frequency it was 250, right? But this time I'm not gonna, it's not loop, we don't have loops, right? So instead of 125, it's gonna be double, because here it's going to be interrupted 2 times. It's going to be interrupts. Okay, so for half a second, to run a signal for half a second, so there should be 250 interrupts. That's why I'm using here 250. For this one, it has to be 500 interrupts. That's why I'm using here 500 interrupts. This is one thing. The other thing, I have to change the frequency. I have to change the frequency every half a second. So this is exactly what happens. After half a second, I'm here. 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 And so, you get what I'm saying? So you have to change the frequency every half a second. Okay. Anyway, very interesting. For sure, you can do little modification in this program if you want to. Number one, if you want to have only one tool. Okay. If it is alarm, in case of alarm, I need 2 tools. If it's alarm. But if, for example, if you have a security system and I enter the PIN number and just you want to make a notification, you want to notify the user, you just give a beep, beep, beep. So it's only one tool. So you can modify it easily here to make it one tune. We can modify it easily to make 3 tunes if you want. It's very easy to use. Why it is very easy to use? Because if you want to trigger the sound, enable the interrupt. If you want to stop the sound, disable the interrupt. You got what I'm saying? So it's like you have a device, turn the switch on and turn the switch off. That's it. The switch here is the interrupt. Okay. Anyway, any questions? Any questions? Okay. The other, I think I explained this one before, but I can go through it quickly. Here, I can use also output compare like RTI, as RTI, okay? So, all what I'm gonna do here, it's exactly same thing regarding configuration as I did before. Maybe the only difference, I'm gonna configure the action to no action because I'm not generating a signal, so there is no need to put here 0 or 1, just no action, okay? And then, for example, here, I want to make interrupt every 1 millisecond. So you need to count. You need to count how many. You need to convert. You need to convert this time to number of counts. So 1 millisecond. Okay, you have to divide it by 1/3 microsecond. How you get this number? Yeah, I got this number because I'm making the brief scale 8. Okay, so this number here, as I said before, should be 1/f, and f should be 24 megahertz divided by the prescale. Anyway, I did the calculations based on this 8. I found it's 1/3 microseconds. That means this 1 millisecond, it means 3,000. Okay, that means the count has to be 3,000, and that's what I did here. Okay, so here I want to make periodic interrupts like RTI every one millisecond. Every 1 millisecond. Is that okay? And then very easy. All what I have to do here in the subroutine, in the interrupt subroutine here, right? All what I'm gonna do is I'm gonna say TC, whatever channel you are using, should equal TCNT plus interrupt period, which is 3,000. That's okay. That's it. So every interrupt, you are gonna say, please, next interrupt after 3,000 counts. Once you come here to the interrupt, please, next one after 3,000. Okay. Again, this is very interesting. I like it more than RTI. Okay, because you can change, as I said before, fine grain. What I mean by fine grain, you can change the time out by the scale of 1/3 microseconds. So every time I add 1 here, I actually add 1/3 microsecond. Is that okay? So you can change it easily, more than we have better than RTI. Anyway, okay. So if you want to make interrupts instead of 1 millisecond, I want to make it every 2 milliseconds. For example, I can change this number to 6,000. Is that okay? But again, keep in mind you have a limit. Keep in mind, remember, you have a limit. What is the limit? I cannot make this one more than 65,535. So this is my limit. So for example, if it is 60, for example, if I go for 60,000, so I think this one is going to make 60 milliseconds, right? So I think, yeah, because is that right? Or I think I'm wrong, right? This one is going to make 5 milliseconds, because 3,000 is making, yeah, I think it's 5 milliseconds, 5 or 50. Yeah, I think 50, right? 50. Anyway, you can multiply it by 1/3 microsecond to get the exact time. So it's gonna be, sorry, 20, right? So anyway, you will see right now. So 60 divided by 2 is gonna be 20 milliseconds. Is that okay? So if I put 60,000 here, so I can make it 20 millisecond interrupts. Yes.
That should be DC.W, right? Instead of DC.B, we're doing 65.
Oh, you're right. I'm wrong. You're right. Thanks. Yeah.
I just want to make sure.
No, you're right. You're completely right. So because this one has to be a word, I'm sorry, I'm gonna correct it. This one is a W for sure, because this one has to be a word. Yes. Okay. Because TC is a word, TC and T is a word, and this one is a word. Yeah, you're right. It's a mistake. I'm gonna correct it. Thanks. Okay, guys. So that's very easy to do. The last program I want to teach here before I go to pulse width modulation, very interesting program. Okay, so based on what I said, based on what I explained right now, guys, is I told you, let me. So as I explained to guys, if I want to generate a signal like this one, so this part, I'm gonna have something like high count, as I said, okay, and then I'm gonna have something like low count, which in the program I did, this one was 2100, this one was 300. Is that okay? So because I need here, this one was 100 microsecond, this one 700 microsecond. Anyway, so the question is again, there is a limit. There is a limit. I cannot exceed. Again, what is the limit? I'm limited, okay? That means this high should have a maximum value. This high should have a limit. The limit, again, I cannot put here more than 65,535. This is the maximum value I have, right? That means, okay, so you have some kind of a limit here. So for example, if I use 1/3 microsecond, and if just to make the calculation easy, so I'm gonna make this one 60,000, that means the limit 2 milliseconds, right? So I cannot generate a signal bigger than 2 milliseconds. 2 or what? 20, right? I'm sorry. Yeah, just to multiply, right? Because this is the number of counts, which 60,000. Every count is 1/3 microsecond, right? So if you multiply it, it's gonna be 20 milliseconds, okay? So if I use the maximum number I have, I'm gonna generate a signal that is 20 milliseconds and 20 milliseconds. Oh, is that okay? Is that okay, guys? Okay, but that's too bad. Why it is too bad? Because it's very restrictive, very limited, okay? What if I wanna generate a signal like 1 second and 1 second? 1 second. Okay, what can I do? That doesn't mean I cannot do it. No, you can. And that's what I'm gonna explain the idea right now. Okay. So again, my limit is 20. My limit is 20. Okay. But how I can do something like that? How I can do something like that? I'm gonna tell you how you can do it. Okay. You know, this problem is similar to another problem I explained in chapter 4. This problem, you remember RTI, the maximum time out. The maximum time out for RTI, it was 131 millisecond. You remember this one? And I told you how I can make 1 second to turn it on for 1 second and off for 1 second. I have to respect the limit. I have no choice. I have to respect this limit. So what I did, I had interrupts here every 131, and then I counted. Interrupt number 1, do nothing. Interrupt number 2, do nothing. Until interrupt number 8, because at interrupt 8, I actually make 1 second. Is that okay? I'm gonna use the same idea right now. I'm gonna use the same idea right now. Is that okay? So okay, first, let's think about it. Okay. So first, for example, if I use 1/3 microsecond, okay, and if I use 60,000 count, that means next to toggle, if I'm here. That means next toggle, I'm gonna toggle next time after 20 milliseconds. Is that okay? You are gonna toggle after this one, okay? So the way I'm gonna do it is, look here. I don't need to toggle after 20 milliseconds, okay? For example, if I wanna generate, for example, 200 milliseconds. I'm gonna explain the idea, you'll understand it. It's very interesting, okay? So if I wanna generate something bigger, like 200 milliseconds, how I can do it? I'm gonna tell you how you can do it. Once I come here, okay guys, I'm gonna say next interrupt after 60,000. 60,000 means 20 millisecond. Is that okay? However, I'm gonna change the configuration of the pin to no action. So here, I'm gonna say after make interrupt after 20 millisecond, however, the action is no action. So I'm not gonna toggle, no action. I'm gonna keep it, okay? And then, so now I make 20 millisecond. And then another one, no action, 20 millisecond. And then another one, no action, 20 millisecond. Okay, until what? Okay, here I need 200. 200 means I need 10 interrupts, right? So I need. That's exactly what I'm gonna do. I'm gonna count interrupts. So this is interrupt number 1, interrupt number 2, interrupt number 3, all the way until interrupt number 9. Okay. At interrupt number 9, I'm gonna say again, next interrupt after 60,000, which is 20 milliseconds, sorry. However, I'm gonna change the action here. I'm gonna say the action here next time is pull low. You got what I'm saying? So is that difficult? You got the idea? Let me say the idea again, guys. Again, if you select the action toggle, so your maximum, I'm gonna toggle after 60,000, for example. Okay, it is 65, but just to make the calculation easy, 65,000 or 60, very close. But anyway, let's make it 60. 60, that means the biggest I can get here 20 milliseconds, because it's gonna toggle after 20 milliseconds. So what I'm gonna do, I wanna make it like 200 milliseconds. Okay, so what I'm gonna do, for sure, I have interrupts. I'm gonna get interrupts every 20 milliseconds. Okay, so all what I'm gonna change, that means to make it 200 milliseconds, that means I need to have interrupt 1, interrupt 2. So every interrupt here is gonna be after 20 milliseconds, as I explained, which is 60,000. Okay, so I'm gonna count interrupt 1, interrupt 2 until interrupt 10. At interrupt 10, I have to pull it low, right? So I have no choice. I should have interrupt here, interrupt here, interrupt here. However, now I'm gonna only play in the action. Okay, so I'm gonna say, please, here I'm gonna say, next interrupt after 20 milliseconds. This is my limit. However, the action on the pin, no action. Here, same thing, no action until not 10, the one before 10. Okay, so the one before 10 at number 9, I'm gonna say next interrupt after 20 milliseconds. However, the action is below. So this one is gonna pull low in the next one. Okay, so I'm gonna show how I did it. Very interesting. By this way, you can make it big signals, because we have limits. Anyway, so I have a program. I made a program to have a wave signal. This signal is 1 second and 1 second, 1 second high and 1 second low. Okay, so again I wrote it in C, and I think it's only in assembly. There is no C, but anyway, it's very easy. If you have C, you can make it assembly. You can make assembly. You can make it C. So the way here I used different numbers than what I used in my explanation now. So the number I used here, it was look here. So here we're gonna have interrupt every 43.6 based on the number we have here. That means I wanna generate 1 second. So if you wanna generate 1 second, you should have 23 interrupts. 23 interrupts. Is that okay? Similar to what I explained right now. So I'm gonna count interrupt 1, interrupt 2, interrupt 3, interrupt 4, no action, no action, no action, until interrupt number 22. In interrupt number 22, what should I say? Next interrupt, please, the action is pull low. Okay, or pull high. If it is high, pull high, or pull low. Okay. Also, once I come here, I have to say now the action is no action. So here I'm gonna say no action, right? So this is one thing I have to do. Also this one here. So I'm gonna show you how I did it, guys. So here, this is the interrupt subroutine here. That's very easy. All what I did here, every interrupt, I'm gonna increment a counter, okay? And now I'm gonna compare it to 22, okay? So it can be below less than 22. If it is less than 22, so I'm gonna go to end. As you see here in the end, I'm gonna say TC5 should equal TCNT plus count. Okay, I think this is a mistake, sorry. This is the interrupt period. I define it up there. Yeah, here. So I'm gonna say make interrupt, next interrupt should be after 43 millisecond. Is that okay? So here, and then I'm gonna leave. So here, so if for all the interrupts from 1 until 22, before 22, that's all what I'm gonna do. In every interrupt, I'm gonna say, please, next interrupt after 43. Okay, and then next interrupt after 43. Okay, this should happen from interrupt 1 until 22. Now, at 22, what should I do at 22? That's what I want to show you. Now, if it is equal to 22, at the interrupt 22 again is the one before the last one. Okay, at 22, I'm gonna go to here at the interrupt number 22. So what I should do, look here, guys, I'm gonna say, for sure I have to say if the signal is high or low. So if the signal is low, I'm gonna change the action. I'm gonna change the action. I'm gonna say, yes, next interrupt is the action bull low or bull high. So if the signal is already high, I'm gonna say bull low. If it's already low, I'm gonna say next time bull high. Okay, that's what I did here. So I already have one variable to tell me the signal high or low, and then if it is low, I'm gonna come here to change the action. Remember, this action is gonna be taken next time, next interrupt. Okay, so next interrupt, the action will be low. Okay? Or high if it is in the high. Okay, now, so I said if the interrupt is equal 22, in case of 22, I'm gonna come here. Here is 22. 22, all what I'm gonna do in 22, I'm gonna just change the action, okay, for next time, okay? However, if it is less than 22, just I'm gonna come here and then I'm gonna leave. Okay, what about if it is 23, at 23? Last one, 23. What should I do at 23, as I said? Okay, remember, at 22, I made the action, I changed the action to be low. Pull it low. At 23, I have to return it again to no action, right? And that's what I did. So if it is 22, 23, so number one, that's what I'm gonna do. Number one, I'm gonna return the action again to no action. Also, I'm gonna clear the interrupt counter because I need to count for another 23. Okay, this is similar to what I taught in chapter 4 when I said when you counted for 8 interrupts. After 8 interrupts, you have to clear the counter to count for another 8. That's what I did. So here, after every 23 interrupts, I have to clear to count for. Very interesting because by this way, otherwise, if you don't do that, it's going to be very restrictive. Your maximum, the big signal you can generate is just a 20 milliseconds, right? So very restrictive. Okay. Anyway, any questions? Okay. Anyway, I think this is a test. This is test 2, so I don't need to explain it. And I think I explained this one before, and I told you all what we need to measure this time. gonna tell you why. You will like it, okay? I'm gonna tell you what is this, okay? As I told you guys, our microcontroller, it's a complete system. That's what I said in the first lectures, in the first week or second week. I told you microcontroller is a complete system, okay? This system should have microprocessor, and it has timer system, it has analog to digital, it has a lot of stuff, right? Okay, so one of the things here inside the microcontroller, a circuit, this circuit is called pulse width modulation. Pulse width modulation. I'm gonna tell you why is he call it this name. Anyway, so I have a circuit here, we call it pulse width modulation. Number one, tell us what is this, okay? When we can use it, and how, and what this one can do better than what we taught before, okay? I'm gonna tell you this, okay? Number one, what is pulse width modulation? Pulse width modulation is a circuit that can help you to generate a square wave. So you can so if you want to generate a square wave, you can use this one. Okay, but we already generated square wave before in this course 2 times in chapter 3, and in using output converter. What is the difference? I'm going to tell you what is the difference. Okay, so number one, this one is used to generate a square wave. Okay, number two, here, and this is the main advantage. The main advantage here, it's very easy to change the frequency if you want, or to change the duty cycle. This is the main thing. Very easy to do that. What do you mean by change the duty cycle? It means, for example, I can generate a signal like this one, okay, and then very easy, I can make it bigger a little bit, like something like this, okay. So now I'm increasing the duty cycle, right? So now I'm increasing, and so on. So it's very easy to do that. In some application, I need to do something like that. Okay. In some application, I will give you some of the application. In some application, I need. That's why it's called pulse width modulation, because that's exactly what I'm doing here. I'm doing modulation. Okay. Modulation how? So as the value increases, okay. So you have some value, you can increase the weights as you see here. So it's a kind of modulation. Okay. You can increase the weights here. But this, you can do it here much easier, much more efficient than what we did before. Okay, this is pulse width modulation. Number one. So let me tell again. First, what is the sign up sheet? Is that somewhere here? Sign up sheet. It's here. Okay. So, okay. Number one, you are telling us, pulse width modulation is a circuit that can be used to generate a square wave, okay? And you are telling us, number one, this one much better than what we did before, but you didn't give us details. I will. Number two, you didn't tell us. Also, you told us the main advantage here. It's very easy to change the duty cycle. Very easy. Okay. So number one, to tell us how this one different from what we did before. I'm going to tell you. Okay. How can you generate a square wave? In digital systems or in computer systems, in many applications we need to generate square waves. Okay, so all the time we generate square waves. So it's very important. We use it a lot to generate square waves. So to generate square wave, we did in this course, we did it 2 times by 2 different ways, and the pulse width modulation is the third one. Okay, I will show you right now. In chapter 3, we generated square wave this way. You remember when we did turn LED on and then wait 1 second, and then I said turn LED off and then wait 1 second and then loop back. Okay, that's what we did in chapter 3. Okay, when we did flashing, it was a square wave. Okay, but this is too bad, right? That's what I said. We shouldn't use it this way. Why it is too bad? Because because the CPU was busy all the time, right? So CPU was busy all the time, right? So that's why it was not a good idea, because this one takes too much time from the CPU, okay? And then we came to chapter 5. You told us I have a better idea than this one. So we have a better idea. I can use output compare, and that's what I have. That's what I explained last lecture, and also this lecture. You told us I can generate a square wave using output compare and using interrupts. That's true. And you told us I'm gonna take only you are gonna have interrupt here, interrupt here, interrupt here. So you are gonna take just little time from CPU, right? So I'm gonna take just a little time to serve the interrupt here and serve the interrupt here, serve the interrupt here, okay? Because the difficult work is done by the circuit, by the timer circuit, counting from here to here. CPU is not gonna count. This counting is done by the external circuit. Same thing, counting from here to here is done by external circuit. All what I need from the CPU, just little bit, some time to execute the subroutine. Instead of this one, the CPU was busy all the time, right? No. All of them here, sometime here, sometime here, sometime here, sometime here. Okay. So number 3, pulse width modulation. Okay. Okay. How this one is different? I'm gonna tell you. So number 3, pulse width modulation. Okay. Even this one, we can even improve this one more. So we can improve this one more, because remember, for interrupt, if you go back to when I explained interrupt, there is overhead associated with the interrupt. Even if your interrupt subroutine is empty, even if it is empty, just when you trigger interrupt, okay, number 1, automatically you have to push all the registers. Okay. Number 2, I have to pull all of them back. Okay. So there is already overhead, already computation. On top of that, I have to execute some code in the interrupt subroutine. You got what I'm saying? So how pulse width this one, it doesn't look bad. Yes, it doesn't look bad, but this one is much better. Okay. So how this one is different? I'm gonna tell you how this one is different. But number 1, don't be confused, because I have been teaching interrupts for some time. This one, pulse width modulation, no interrupts here. Don't be confused. No interrupts here. So this topic has no interrupts. Okay, because I have been teaching interrupts for several weeks. Interrupt. So you may think this one has no, this one doesn't have interrupts. Okay, this one is gonna very interesting. Gonna do some magic. I'm gonna tell you how. Okay, so what happens is that this is the CPU, and this is the pulse width modulation. All what I need from you, my friend CPU, all what I need from you CPU, just initialize or set the parameter here. Set the registers here. Once you initialize, this one is gonna generate a square wave forever without involving the CPU anymore. Very interesting. You got the idea? So it's different from here. Here I need CPU here. I need CPU here. Here I don't need the CPU. Once you initialize it, the circuit is gonna generate a square wave forever, and I don't need the CPU to get involved. I need zero time after the initialization. I need 0 time from the CPU. Is that okay? Unless you wanna do something like, for example, here once I initialize it, it's gonna trigger a signal this way. Okay, how much time after the initialization? Do you need any time from the CPU? No. The circuit is gonna take care. The external circuit is gonna take care of is gonna generate it. Okay. However, if I need to change it, yes, at this time I need the CPU to change, to write some instruction to the registers to change the period. So this is so if you don't want to change the period, just I need the CPU to get involved. Just if you want to change the period and so on. Okay. So any questions? Okay. So let me tell you the conclusion again in one sentence very quickly. So pulse width modulation, you told us number 1, no interrupts. Yes, no interrupts here. You told us number 2, after initially, what you need from the CPU just to do initialization. After initialization, So you are going to generate this signal is going to be generated periodically forever, and you are not going to take any time from the CPU. Yes, because this one will be done by the external circuit. Okay, 0 time from the CPU after initialization. However, if you want to change something, CPU has to go and to change the initialization. So, okay, so if I want to change the frequency, if I want to change the duty cycle, I have to go and change the initialization here and then leave it. Okay? Also, I said in many applications, I need to generate square wave, and also in many applications, I need to change the duty cycle. I'm going to give you some application today, but in many applications, I need to change this duty cycle, okay? This one also is used in servo motors, right? You program the servo motor, right? You understand how you use something like that? Yeah. Use the pulse width modulation or use something else?
You needed to make the servos move, you need to change the duty cycle.
That's okay, yeah. So in order to run the servo motor, you need to change the duty cycle, yes, okay? And pulse width modulation is perfect, easy to do it. You will see right now why it is easy, okay? And other applications, not only servo motor, also other applications using pulse width modulation, okay? So I'm gonna give you more details now, but this is the main thing. So another application like what? I'm gonna tell you, for example, here, as you see here, guys, as I go this way, I increase the duty cycle. When you increase the duty cycle, you actually increase the average voltage, okay? In some applications, like for example, when I increase the, if I apply this signal on this bulb, you can increase the lighting. So this one can be used if you want to make it dim. So the lighting you can by increasing the voltage by increasing the duty cycle. If I go this way and increase the duty cycle, you increase the voltage. When I increase the voltage, you actually increase the lighting. Okay? Same thing for the, if you have a fan here, you can make it spin faster, okay, when you increase the frequency. Just some application, and for sure, I think the other application, as I explained, the servo motor, okay? So let me tell us, okay, so here, again, don't be confused, I'm gonna say it again, we don't have here interrupts, no interrupts here, okay? So number one, how many? We have 80 channels, as you see here. 80 channels, every channel can generate a signal if you want. So we have 80 channels. These channels are connected to port P, okay, as you see here. These channels are connected to port P. That means every pin on port P can generate a signal, different signal for sure you can, or similar, whatever you wanna do it, okay? Number two, every channel should have two important registers. So we are gonna use them. One is called period register and one to control the duty cycle. Again, every channel should have two registers. One to control the frequency, the other one to control the duty cycle, okay? And why I'm saying one of the magic things here is you can easily change the frequency or you can easily change the duty cycle. Why it is easy? Because just I put some number in the register. If you want to change the duty cycle, just change this number in the register, which is very easy. We have in all this course, we are just changing numbers in the register. So it should be very easy, right? So how it works, how the pulse width modulation works, as I told you, every channel should have two registers. One register, we call it pulse width modulation period. We have period 0, we have 0, 1, 2 until 7. Okay, so we have eight registers. Pulse width modulation period, and the other one pulse width modulation duty. Okay, this one for the duty cycle. Okay, how it works? What is the main idea? I'm gonna tell you how it works. Number one, I should have a clock. Where this clock is coming from, forget it now. I'm gonna give you details. Okay, so I have a clock, some clock. Okay, and then I have two registers. This register and this register. All what you have to do is just write some number here and put number here. For example, if I put here 50, if I put number 50, what it means? It means from here to here, the time from here to here, it has to be 50 cycle from here, 50. You got them, say 50 cycle. So I have a clock. This clock, I'm gonna use it like a reference, and then the number I have, I'm gonna write here. This number should give you, for example, if I say 50, if I put here 100, for example, 100, that means the time from here to here should be 100. 100 cycle. Is that okay? That means, that's why I'm saying, if you want to change the duty cycle, all what you have to do, very easy, very, very easy. All what you have to do, just change this number. If I put 10, now the duty cycle is 10%. If I put number 20, now it's 10 to 20%. If you put 30, 30%. Just a number you write in a register. So that's why it's very easy to change the duty cycle. Is that okay? For sure, if you want to change the frequency, you can change this one. This one is going to change the frequency. This one is going to change the duty cycle. Is that okay? This one is going to change how big is the high, the high part of the signal. Okay. So now that's all what we have. We have we have a clock. I'm going to tell you how we can get this clock, and then we have two registers. In every register, you have to write a number. This number using these two numbers is relative to the clock we have. We can generate a signal, something like that. Okay. Another important thing you should understand, when I put here 100, what it means? It means for 100, for every 100 cycle here, I'm going to generate one cycle here. What it means? It means it's like you divided this frequency by 100. Okay, so it's like you divided it by 100. Yes, it is division. Why you divide it? Because for every 100 here, I'm going to generate only one here. Okay, so it's like you divided it by 100. Okay, for example. So number one, now what I'm going to explain is, okay, number one, how can you get this clock and can you program this clock? Okay. Similar to what I did in the timer system. Okay. Don't be confused. The timer system is completely different from pulse width modulation. Nothing is related. Okay, they are completely different things. Maybe the name of the maybe I made a mistake in the name of the chapter. I call it timer system, but it has. Four, not two. One is called clock A, as I said. The other one is called scaled clock A. Same thing we have here, clock B, and we have scaled clock B. Okay. For this one, it's exactly the same thing. It's 24 megahertz divided by prescale, but this prescale is different from prescale. This one is different register, so you can put different values if you want. Okay. And then you divide it by n. This n is different register. So this is a register, this is another one. Okay. By this way, guys, you are gonna have four clocks. These two clock, this one and this one. they are used for channel 0, 1, 4, and 5. So for every channel you can select. I'm going to show you later how can you select. For this channel, please use this clock. For this channel, please use this clock. For this one, use this clock. For this one, use this clock, and so on. Okay. Same thing here. So we have 2 options for every channel. It has 2 options. For 2, 3, 6, 7, you can have one of these 2. Is that okay? So here, I told you. Let me say here. Look here, guys. I told you the frequency here should be 24 megahertz divided by prescale. Is that okay? And the frequency here should be 24 megahertz divided by prescale, okay, times n times 2. Is that okay? So this is the clock. This is the clock. So I told you the frequency here, what I get here, should be the same frequency here divided by the number I put here. That's what I told you, right? So I told you if I put here 100, so actually if this is f, so what I'm gonna get here, f divided by 100. Is that okay? Because you are gonna divide it by 100. Why you divide by 100? Because for every 100 cycle, for every 100 cycle, we are gonna generate 1 cycle here, okay? So if I wanna get, so what is the frequency I can generate? The frequency I'm going to generate, this frequency is the clock divided by the period, which I said 100 here. Yes. So this one or this one, because I have 2 clocks now. So you can select this one, any one of these 2 clocks, this one or this one divided by period. That's what I put here. So the frequency I can get, is going to be the frequency, the clock divided by period. Or in case of scale to clock, it's going to be this one here divided by period. Okay, is that okay? And then all what I'm going to do now, I want to find what is the maximum frequency I can generate and what is the minimum frequency. So let's look here. What is here? Look here, guys. How I can get maximum frequency. So I will try find the maximum value here and maximum value here. Okay. Sorry, maximum frequency, it has to be this minimum value here and minimum value here. The minimum value here is 1. Minimum value here is 1. That means the maximum frequency, if I select clock A, the maximum frequency I can generate from the pulse width modulation is 24 megahertz. Okay, and now let's look at the minimum frequency. For the minimum frequency, I'm gonna put here maximum value, which is 128, and then I'm gonna put here the maximum value, which is 256. Okay, 256. So if you look at the result, this is the minimum frequency I can generate. So conclusion. If you want to, I told you we have 2 sources of clock, and for every channel you select, you want to use this source or that source. Is that okay? Based on what you select, I'm going to tell you based on what. Based on what is the frequency you want to generate? Because if you select the clock A, in case of clock A, this is a range. I can generate frequencies from 732 hertz to 24 megahertz. Okay. If your frequency outside this range, you cannot use clock A. Period. Right? So this is the range of frequency I can generate using clock A. Okay? For the second one, I should generate lower frequencies. Lower. Why? Because here I divide it by more numbers. So I can be lower. Yes. So if you see the range here, the range can go from 12. This is my maximum 12. Why 12? Because I'm gonna put here 1, 1, 1. I have 2 here, right? So it should be 12. 24 divided by 2 is 12. So 12, and the minimum frequency, it can go to only 2 hertz. This one is 700 hertz. Was that okay? So conclusion, what's the conclusion? The conclusion is, this is the range of frequencies you can generate using clock A. This is the range of frequency you can generate using scale to clock A. So every channel, for every channel you can select, every channel, this channel, you can use this one or you can use this one for every channel, okay? I have to select based on what? I have to select based on what frequency you want to generate. You have to make sure the frequency you want to generate should be in this range, otherwise it's not going to work. Same thing here, it has to be in this range, okay? You can see this one, you can go to only very, very small value, 2.8 hertz, very, very small, right? This one up to 700, okay? Okay, now let's go to programming. How can we program the pulse width modulation? The first thing I'm going to explain, I told you here we need to have prescale here. Yes, So where I can find these two, okay? And where I can find this one as well, this is the name of the register. Whatever you write here, this is a byte, right? This is a byte register. It's a byte, okay? Someone can tell me, there is a tricky point here. The tricky point is that this is a byte. Any byte should have a value from 0 to 255. Now you are saying 256. Doesn't make sense. You got what I'm saying? Because if it is a byte, my maximum should be 255. It shouldn't be 256. Okay? I'm gonna tell you how they made it. The way we made it, 0. We're not gonna use 0 because you are not gonna divide by 0. I'm not gonna divide by 0. So the 0 actually, so it's actually from 1 to 255. And 256 is 0 actually. So they used the 0 for 256. Because you got what I'm saying? So it's from 1 to 56 because the 0 is gonna be 256. Because I'm not going to use 0, right? I'm not going to use 0 because you cannot divide by 0, okay? So this is the name of the register, which is a byte. This is the name of the register. But tell me, so all what I need to know here, number one, this is just a name. This is the name of the register you can use. This is the name of the register, similar to the registers I used before. This is just a name. You can use this name, okay? All what I need to tell you now two things. Number one, tell me, where are these prescale? In which register I can find these prescales? Is number one. Number two, you told me every channel can select clock A or scale to clock A. Tell me how I can do that, okay? Let's see here. So number one, this is the first question. So in the first question, we have this register. This is the name of the register here. This register, we have 3 bits for one prescale. We have 3 bits for the other prescale because I told you we have clock A and clock B. For every clock, we have 2 types. So actually, we have 4. Yes, we have 2. We call them A and scaled A. We have another 2 B and scaled B. Yes, but these 2 are used for 4 channel, and this one are used for another 4 channel. The other 4 channels. Okay. So here, this is the name of the register. These 3 bits are for the one prescale. For clock A, these are used for clock B. Very easy, right? This is just a register. You can just write some numbers in register. We have done this many times, okay? Number 2, you told us, I can select every channel, I can select. If this channel should use clock A or scaled A or clock B, how can I do that? Very easy. Again, similar to what we did before, I'm gonna have a register this way. Every channel has 1 bit here. So this is for channel 0, channel 1, channel 2, until channel 8, channel 7, sorry, from 0 to 7. So for every channel, here you can select, do you want a channel 0? Okay, so here, again, so this is for channel 0145, okay? A channel 0145 can select either A or scaled A, okay? So if I put here 0, so I'm gonna say channel 0, please take from clock A. If you put 1, please take from scaled to clock A. Is that okay? That's it. So every channel has 1 bit. Using this bit, I can select for this channel, should you get it from the clock or from the scale to clock. Is that okay? The other register I have here, we call it enable or disable. Okay, let me ask you a question. If I initialize the pulse width modulation, and now I generate a signal. So after I generate a signal, so I have no control in the signal, I cannot stop the signal because no interrupt is here. Again, in output compare, if you want to stop the signal, you have to disable the interrupt of output compare. Here there is no interrupts. So once I generate it, I have no control in the signal and it's gonna continue forever. I cannot stop the signal. The answer is no. That's why we have this register. So this register, for every channel we have 1 bit to turn the signal on or off. Right? For some reason, I generated the signal, and now I want to turn it off. Okay? So how I can do that? Here, again, in output compare, I can do that by disabling the interrupt in output compare. Okay? Here, I have to do it using this register. So I have here a register. We call it enable register. Again, no interrupt. This is not interrupts. Okay? So every channel has 1 bit, as you see here. So if I put 0, so actually I'm gonna disable. If you put 1, you enable. What disable means? Disable means no signal. Okay, no signal. I'm not gonna stop the signal. No generation to the signal. Enable means you generate the signal. Okay, very easy. So we have 8 bits here. Every bit you can enable or disable the signal. Another one here, which might not be very important, but I'm gonna explain it. One we call it polarity. Polarity. The signal you want to generate. You want to generate a signal this way, or you want to generate the signal this way. Okay. Here we call the polarity is 1. Here the polarity is 0. So you can generate this way or this way, whatever you like. Okay. So this is the duty. So here, this is the part. What I explained to you before, I told you this part. This should be in the duty cycle register. But here, if you flip it, so here, this part, this is what should be in the duty cycle register. Okay. So how I can do that? Again, we have here this register is here. All what you have to do just to put 1 or 0. So for example, this is channel 0. I'm gonna put here 1. Or you can put, if you want to generate 1 if you want to generate signal this way, 0 if you want to generate signal this way. Okay. The last one here also again alignment. So the last one here is alignment. You can generate the signal. You want the signal to be left aligned or center aligned. Okay. This is the signal left aligned. So it's gonna be this way. If it is center aligned, so it's gonna be this way. I'm gonna generate the signal this way. So it's gonna be like, okay. So it's going to be, this part is going to be repeated. We call it center aligned. I don't know how this will be. It depends on actually application, but I think most, if you just need a signal, you can just use this one. Okay. Okay, now, let's come to how can you program it? How can you program it, okay? Let's see, for programming, if you go back here, number 1, I have to decide what is prescale you are going to use. Number 2, you have to decide what value you have to put here to generate a certain clock here. Okay. Once you know what clock you have, you can decide what values I have to put in the duty cycle, what value I have to put in the period to generate the required frequency. Okay. And then you can just write here the values. Also, you can write here where you want to get the signal from, which clock. For sure, in the beginning, you have to enable, and then if later, if you want to turn it off, you can turn it off. You can select polarity. That's all what you have to do. Once you do that, once you do the initialization, you are done. CPU doesn't need to do anything else. The signal is going to run forever, unless you want to change the duty cycle. In this case, CPU has to go and write and change the initialization. It has to go and write some value in the duty cycle. Okay. So let's see, I'm giving you here one example. If I want to generate, then I'm going to show one program. Very easy. You will see it right now. Very easy program. It's very easy to program it. Once it's just a bunch of numbers. Once you get this number, write the number in a bunch of registers. You are done. That's it. So number 1, I have to get some numbers. Number 2, I have to write this number in register. Once you do that, you are done. Very easy, right? So I'm going to give you example here. If I want to generate 100 kHz frequency, 100 kHz this way. So for example, let's look here. If you look at the pulse, if I use clock A, can I use clock A or scale to clock A? Okay, number 1, how I can know if I'm gonna use, can I use clock A or scale to clock A? The answer is yes. You go to look at the range here. 100 kHz is in this range. That means you can use clock A. Can I use scale to clock A? Yes, because it is in this range. So it should work. It should work for any one of them. Yes. Okay. So what I did, I just put here here. Look, very easy. This is the signal. For example, if I select clock A, first I make sure this frequency is in the range of A, so I can get it from clock A. This number 1. Number 2, if I put here 100 kHz, okay, and then I have 2 unknowns here. Okay, so here if I do just multiplication, I found in order to get here 100 kHz, the multiplication of these two registers should be 240. Okay, so any value, and then it's up to you. Select any values. Select any values here, so that their multiplication should be 240. That's it. Okay. So for example, one option, so you have too many options, right? Sure. I can put here 1. If I put here 1, so this one has to be 240. Yes. Or I can put here 2. If I put here 2, so this one has to be 120. Okay, that's it. Again, all what I have to do, I want to get bunch of numbers. Okay, once I have these numbers, I'm gonna put them in register and then I'm done. Okay. Okay. Now, what about if you want to generate 50 kilohertz? 50 kilohertz. Okay. Same thing. I'm gonna put here 50 kilohertz. Okay. And then I will find the multiplication of these two should be 480. Okay. Remember, every one of them, this one has a range. This one also has a range. You should not exceed this range. So this one should be, this is the range for this one. It can take 1, 2, 4, 8, 16, and so on. This one should take a value from 1 to 256. So you have to respect this range, okay? So if I want to generate 50 kilohertz, so the multiplication of these two should be 480, okay? Can I put here 1? Can I put here 1 and put here 480? No, you cannot. Why you cannot? Because the maximum of this one should be 256. So one is not gonna work. Okay, for Bris scale. So, but can I put here 2 in Bris scale and put 240 here? Yes. Can I put 4 and 120? Yes. Okay. Anyway, so using this equation, you should get some numbers. And then what I want to explain right now is, after I get numbers, just write this number in registers. After that, you are done. Very easy, right? I'm gonna explain this program for C language. For C language, number 1, you can do the same thing like assembly. You can just write some number to register as we did before. So I can write here some number to register, or I have a number of functions. You can just use these functions if you want. Okay. So I'm not gonna explain the functions. They are just very easy. So let me explain now. For example, here, guys, I want to generate 100 hertz frequency. The duty cycle is 50%. I want to do something like that. Okay. So number 1, I have to do some calculations. I'm going to use clock A. So that means, and then based on that, I'm going to put here here 2, and this one has to be 120. Okay. And now, so the period is 120. Okay. In order to make 50% duty cycle, so the period, I have to put 60 in the period, okay? So, and that's what I did here. Look here, guys. In the period, I wrote 120. In the duty cycle, I put 60. Remember, this is the period for 0. We have from 0 to 7, okay? So this is very easy thing to do. Another thing you do, number 1, because you are selecting clock A, so I have to select the clock A here, okay? Because the Bris scale is 2, I have to do it here. Okay, so I have to write 1 because the Bris scale is 2 to power I is 1, so this can make Bris scale of 2. I have a polarity. You can set the polarity as I explained. Also, you can make it left aligned. Okay. Also, I'm gonna explain this 8-bit mode. That's it. Once you do this initialization, this is the interesting part, guys. Once I finish this initialization, now you are going to generate a signal forever. And you don't need to do anything else, just done, right? Now, if I decided I want to stop the signal, and I'm asking here in your program to use a button to turn on and off. So here, I'm going to see I'm going to use a switch. So if the switch is 1, here, just as I told you, just one bit. If I put 1 on, 0 off, that's it. So here I can turn the signal on and off. That's it, okay? For sure, this is the beauty here. This is the beauty. The beauty is, now, the period is 120, okay? By changing this number here, okay? If I make it 60, that means it's 50% to do the cycle. If I make it 30, so that's what I'm saying. That's why it's very interesting. It's very interesting because if you want to change the duty cycle, it's very trivial. All what you have to do, just to change this number here. You can come later and change it to 30, to 20, to 40, to 50. That's it. So by changing this number, you can change the duty cycle. Very easy. Just register. You write some number to register. Is that okay? Anyway, so here, nothing is important here. This is just another program. This also just very easy to learn. This one here, I want to make a dim. I want to make this light dim. So what I do here, every 100 millisecond, I reduce the duty cycle by 1. So actually, you know, this is as I increase the duty cycle, I can increase the lighting. So if I go this way, I increase the lighting. If I go this way, I reduce the lighting. So I can make it dim. Okay. That's what I'm doing here. So every here I'm doing it dim. So every 100, I want to make it dim gradually. So you can see the lighting is decreasing gradually or increasing gradually. Okay. So here every 100 millisecond, I'm going to decrease the duty cycle or increase the duty cycle. Also decrease here. Okay. Or you can make it increase if you want. Okay. This is the assembly for this one. The last thing I want to explain here, shouldn't take more than 1 minute. Okay. This is also an option. Listen to me. This is an option. What I explained before, we call it 8-bit mode. Okay. Why it is 8-bit mode? Okay, because the duty cycle, because the period and the duty cycle are 8-bit. Okay, there is one option here. So the duty cycle is 8-bit. The period also is 8 bits. Okay, the size of the register. There is an option here to concatenate. You can concatenate two channels together to create a bigger. You can make the duty cycle bigger. Also, you can make the period bigger. So here again, what I explained before, we call it 8-bit because the period register, it was 8-bit. Now we have an option to concatenate two channels together. So I can get channel 0 and channel 1, concatenate them together. Why? First, what do you mean by concatenate? What I mean by concatenate means, okay, I need the period register to be 16 bits instead of 8. So I'm gonna take the period register from one channel, the period register of the other channel, I'm gonna concatenate them to make them 16. But why you wanna make it 16 instead of 8? Okay, I'm gonna tell you why. Because if you go back to the formula here, this is the most important part here, guys. If you go to the formula here, if I make this one bigger, I can generate lower frequencies. So this one took a value from 1 to 256. So if I can make this one bigger, I can generate lower. So this is the main point. The main point here, you can use concatenation. Concatenation means I can use two channels to make them like one channel, right? And the benefit here, this period can be bigger, okay? So you can reduce the frequency, you want to generate more. I just want to show you numbers. First, in order to concatenate, this is very easy. All what you have to do, you have here bits, just to put one in the bits to concatenate. That's it, okay? Very easy, right? However, I just want to show you some numbers. Here, if you use clock A, okay, using 8-bit, okay? So that means this is my range from 24 to 700 hertz. However, if you use the 16-bit, 24 will be the same. But look, I can lower it from 732 because this one was 256. Now it's not gonna be 256. It's gonna be 65,536. So you're gonna divide by a bigger number. Okay, guys. Anyway, I think that's the end of this course. Okay. Thanks, guys, for taking this class, and good luck.